Hi everyone. Today I will tell you about our work using vibrations to transport grass parts vertically against gravity. Here's a quick preview of what we were able to accomplish. Before I show you more demos, I want to discuss our model and our high-level strategy for achieving this. We have an oscillating surface shown in gray, as well as a part shown in blue that we want to transport. To the left of the part, we have rollers indicating a low-friction surface on which it slides. We transport the part using two phases, a sticking phase that uses low acceleration, followed by a high acceleration slipping phase, in which the surface slips beneath the part. We get net motion over one cycle, and can repeat this process over and over again in order to transport that part vertically against gravity. However, vertical vibratory transport is much more difficult to achieve compared to its horizontal counterpart. Let's take a quick look at how we can achieve horizontal transport. In fact, we can still use the same sticking and slipping phases that we use for the vertical case in order to propel a part in a desired direction. However, there is a fundamental difference between horizontal and vertical transport. For horizontal transport, we have a symmetric friction cone with an angle alpha on either side of that dotted line. For vertical transport, gravity will tend to skew this friction cone so it is no longer even on either side of the dotted line. We have a smaller angle beta and a larger angle gamma. The effect is twofold. First, we have a more limited peak acceleration that we can achieve during sticking, before we exit out of the friction cone and transition to slipping. This means over a finite distance, if we have a smaller peak acceleration, that we cannot accelerate the part up to as large of a velocity as we might have been able to in the horizontal case. Second, we need a much larger acceleration in order to exit the friction cone when we want to transition from sticking to slipping. Placing some lower bounds on the required normal force, we were able to show that you need a maximum acceleration of at least 2g in order to exit the friction cone. Another consideration for vertical transport is the normal force. In horizontal transport, the normal force is simply a result of the weight of the object. Let's look at how the normal force affects this peak acceleration we can achieve during sticking. So let's say we apply some normal force Fn, and let's assume that this normal force is slightly above what's required to statically hold the part. This means that we can only apply a small acceleration before we would exit the friction cone and transition from sticking to slipping. To avoid this, we can instead apply a much larger normal force, many times that statically required, and this would allow us to achieve a much larger acceleration. However, this also means if we assume a constant normal force, that it's much more difficult to exit the friction cone and transition from sticking to slipping. In other words, there is a trade-off in the normal force we want to apply between the two phases. In our work, depending on the waveform you apply, we were able to show that the optimal normal force is actually several times that required to statically hold the part. And this is one of the key design guidelines that we came up with, in addition to requiring large accelerations that can be reached quickly. In practice, we achieved this using impact-induced accelerations. Moving on to the design of the physical device, we first selected a voice coil actuator in order to create those impact-induced accelerations. Pumping current through the coil would launch this ram at a physical object that we placed in its path, resulting in large accelerations. We then took this motor and we placed it in a rigid platform that is grounded through 3D printed flexures. Motion of the ram would lead to motion of the platform, as seen on the right. To create the low friction surface, we had a springed plate that would apply a constant normal force on the left side of the part. We used this in our experimental setup in order to validate our dynamical model. The experimental setup can be seen on the left, and the view through the phone camera that is pointed through a microscope can be seen on the right. The springed plate is shown in red, the part is shown in green, the high friction surface is shown in orange, and the surface is attached rigidly to the vibratory platform shown in cyan. You can see on the right, in the view through the phone camera, that there are several pencil marks on the three moving parts, the springed plate, the part, and the vibratory platform. We used the motion data from tracking these points in order to validate our dynamical model. A representative experiment is shown here, with the part moving upwards as oscillatory motion of the platform occurs. Tracked surface velocity was used as input to our dynamical model in order to predict part motion. On the left, we have the view through the phone camera, where the tracked part point is circled in red, and the tracked point on the surface is shown in blue. The corresponding colors are shown in the real-time position plot on the right. The simulated part position is shown in black. Moving on from the experimental setup, we decided to create a proof-of-concept gripper that consisted of two of these vibrating surfaces. We tried to transport a variety of parts with different contact geometries, masses, and friction coefficients.